Hello, and thank you for viewing our video on the demonstration of DC grid protection that we're putting out as part of the HVDC technology qualification segment of the final conference build-up for the promotion project. I'll begin by introducing the work package where this work was undertaken. So I'm Ian Cowan, I'm a lead simulation engineer at the National HVDC Centre in the UK, and within project promotion I was the work package leader for work package 9. So within the overall project that you can see here, work package 9 comes towards the end of the technology work streams. And the point of this one is, as the name suggests, is to demonstrate the protection systems that have been developed within the earlier technical work streams. So this will have been covered previously, but just to say that the challenge within DC grid is quite different to AC. The fault current has a very high rate of rise and a high steady state value, and of course there's no natural zero crossing either. Now there's a number of different protection strategies that can be used to overcome this. There's the selective, which is most like what we do on the AC network, where you could protect each individual line or segment. You could use a partially selective scheme where you split the network into different zones, or you can use a non-selective scheme where you would temporarily shut down the whole grid, isolate the fault and bring it back up again, but very quickly. And to achieve these, there's a number of different current breaking devices that can be used. You could rely on the converter AC breaker, but this could potentially be a bit too slow for a DC grid. You could use the fault current blocking converters, or indeed DC circuit breakers. Now, underpinning all this are the so-called intelligent electronic devices, or IEDs for short. Now these are devices that have been under test mainly through work package 9, and these execute the protection algorithms and are the things that instruct whatever your fault breaking device is to operate. Now there's no product readily available off the shelf today on the market, but there's significant development being done towards this end within work package 9 and elsewhere. If the most ready comparison for these IEDs is with like a traditional AC breaker, whereas, and to give you an idea of the challenge for the DC system, for an AC system you would expect the IED to have a processing time of about 40 milliseconds, whereas for a DC IED that has to be reduced down to about 2 milliseconds. So coming back to the work package itself, you can see on the right the symbols for the many project partners that were involved in this particular work package. And as the name suggests, the objective was to demonstrate the operation of the DC grid protection systems that have been developed. We did this by using hardware and real-time testing, integrating the DC systems with the relays themselves and DC breaker models from other parts of the project, brought all these together to develop the DC grid benchmark models, and combining that with test procedures to allow us to perform an assessment of the primary and backup DC grid protection operation. And throughout all this, we've been investigating different elements of equipment interoperability. So the work package was split into many tasks, but it's basically got 3 streams. There's the work done by TU Delft, where they developed the testing procedures. There's the work done here at the National HVDC Centre, where we've been demonstrating the partially and fully selective fault clearing strategies. And then there's work done at SuperGrid Institute in France, where they've been doing more investigation on the non-selective fault clearing strategies. So as you can see from this, all the different strategies and the different fault breaking devices that were mentioned earlier have been covered within work package 9 somewhere. The actual outputs of work package 9, deliverable D9.2 is the actual test procedures that were developed at Delft. Here at the HVDC Centre we have deliverable D9.1, which details the benchmark models. We had an earlier demonstration internal just to show the hardware and loop setup within promotion and test that. And depending on when you're watching this video, we either have the upcoming demonstration event, which is on Wednesday the 9th of September, which you can still sign up to if it's before that date. And this is where we really show the partially and fully selective schemes on a broader network. And then SuperGrid had similar deliverables to us in that there's a report detailing the hardware and loop test environment and a demonstration that they undertook to show the non-selective protection systems in operation. So that concludes the introduction to the work package. I'll now hand over to Marjan, who will give some more details on the test procedures developed, and then on to William from SuperGrid Institute, who will give some more details about the non-selective demonstration that was done, and then it'll be back to me to wrap up the session discussing the partially and fully selective testing that was undertaken and the overall summary of the work package. Thank you.
Greetings from TU Delft. My name is Marjan Popov, and this is a presentation on deliverable 9.2 within Work Package 9 Promotion Project. As I mentioned, my name is Marjan Popov. I work for TU Delft, and I actively participated in Work Package 6 and in Work Package 9. This presentation comprises of several parts: requirements for DC protection, procedures for DC grid protection testing, suggestions on technical guidelines for DC protection testing, and finally the presentation ends up with meaningful conclusions. Regarding the general requirements related to selectivity for fault clearing, they are based on several criteria, as it can be seen in the first column of this matrix, as denoted with blue. These are protection philosophies. Normally, protection schemes could be fully selective, partially selective, and non-selective. Thereafter, we have fault clearing strategies, HVDC grid protection zones, faulted zone isolation method, fault clearing time, and DC line switching equipment. How actually these criteria are divided and depend on a different protection scheme can be seen in this matrix. Regarding the functional requirements for DC protection, because at this moment there is still no multi-terminal DC grid active in practice, these we refer to the AC functional requirements, which are denoted as sensitivity, selectivity, speed, reliability, robustness, and seamlessness. Requirements for DC protection testing will be different, and in order to design them, we need the infrastructure which will be utilized in order to provide the testing. Therefore, we divided this in 3 layers, like hardware platform, software platform, and communication. Hardware platform in this context is very important, and it is also important to have real-time testing methods like RTTS, because it is not only important to see how the relay operates and what the time of operation is, but it is also important to see what the network, how the network will perform after the DC current is interrupted, because we still do not have multi-terminal DC grid in practice, and this is the only way at this moment how we can see the performances of the system itself and the converters and other components. Regarding the software platform, we need to have suitable and reliable DC circuit breaker models, protective function algorithms, power system and control function models, and finally communication. It could be hardware or software defined data transmission network for the links between the hardware platform and the software platform. Procedures for general procedure for DC protection testing are divided in 5 groups according to our investigation. These are fault scenarios, statistical analysis, threshold setting adjustment, criteria checking, report, and troubleshooting. I'm not going to address all of them, but they are actually in detail explained in the report. Regarding the statistical analysis for system level performance, again here we have numerous parameters that we have chosen and which are also important to vary in order to see not only the performance of the protection but also the performance of the system and the associated component within the HVDC system. So these are transmission line type, fault resistors, DC side inductances and capacitances, converter blocking instant, AC system strength, system earthing, and converter topology. Let's have a look in one of these criteria, for example, how we perform the statistical analysis for system level performance. Basically, within RTDS, it is possible to design a C code, and in this code, we can provide an automatic testing of the relays by continuous changing of particular parameters. So based on this here on the left-hand side, we see the flowchart of changing of these parameters. On the right-hand side, we see that based on the selected parameters, we can perform, in this case, 4,500 tests, and that means that 4,500 operation times that we can classify in classes from 1 to M, for example, where class A1 will be the minimum operation time, which is 1.5 milliseconds. And this class belongs to 1.5, and the time increased by 300 microseconds. Then the class 2 can be defined by 1800, for example, up to 2800, and so on and so on. Based on this, we are able to determine the number of operation times belonging to a particular class, and therefore to extract the associated probability. Threshold setting adjustment is also an important part. So in this case, for the system level testing, more influencing factor will be involved, and the corresponding thresholds can be optimally adjusted to achieve better system level performance. We see also on the right hand side the flow chart of the threshold setting adjustment. And finally, criteria for the checking. So in this criteria, we can distinguish correct operations, failed operations, and incorrect operations. Based on this, we determine also the checking of the criteria, which previously we defined as speed, sensitivity, selectivity, security, dependability, reliability, seamless, and robustness, which are denoted by these formulas. The nominator and the denominator can be, of course, extracted from the testing. For example, total number of tests is known in advance, and the results from the where the results that denote the nominator can be defined by the suitable numbers obtained from the testing. Criteria checking, again, here is just an example that we can see for the criteria checking. On the left-hand side is the speed checking, and on the right-hand side is the sensitivity checking. Basically, it is important that we perform all these tests. One important fact here that we should mention is that each test should be repeated 5 times. Normally, this is also practiced in AC testing. And after that, we can obtain the results which are important to define these criteria. Regarding the suggestions at the end, we can summarize all these results within high performance, low performance, and medium or average performance. How we can summarize this, we can explain here shortly. For example, let's consider that we have 9 algorithms, and all these 9 algorithms now are tested for the criteria speed, for example, and let's consider that we have algorithm 5, 3, and 4, which result in 99, 98, and 96%. So we can denote this as a high performance. Thereafter, we have the rest of the algorithms which perform between 89 and 96, which are the medium, and everything which is below 89 can be considered as a low. How we can determine this threshold is not actually to us, it's not standardized, and this will be actually the feeling of the user. So how user would like to define the high performances will fully depend on him. In conclusion, we have several conclusions. As we can see, we can utilize the already available standard procedures for AC protection testing. The specific performance criteria are designed based on a multi-case testing and statistical analysis. Some suggestions here are proposed, and finally, this could be useful for further standardization of the multi-terminal HVDC grid. More about this can be found in the report and in our 2 published papers. One of those is IEEE paper on procedures and assessment in IEEE Industry Electronic Magazine that will be published September 2020, and the fast protection multi-terminal HVDC system based on transient signal detection is a paper that we have realized in another project. However, the model we have also used for testing of protection. Thank you for your attention, and in case of having other questions, feel free to contact me.
Welcome everyone. This presentation is about a demonstration of non-selective fault clearing strategies for meshed HVDC networks. My name is Leon Garcia. I've been working on promotion Work Package 9 on task 9.7 and 9.8, which I will present hereafter. Work Package 9 objectives have been presented previously. Here I resume in keywords the 6 objectives which are related to a hardware in the loop testing, develop real-time simulation models and a benchmark grid, demonstrate primary and backup fault clearance sequences, assess interoperability, and test system recovery. 2 systems have been built and tested in collaboration with RWTH Aachen University, which are the converter breaker protection strategy and the full bridge converter based protection strategy called CBS and FBS for simplicity from now on. First, let's have a look of the HIL setup used for promotion Work Package 9 in SuperGrid Institute. A powerful workstation communicates with a target using TCP/IP to compile and drive the simulated plant, also to receive scope data. The plant is a 4 terminals HVDC network running at 50 microsecond execution time step. We also have an access to the IEDS cluster from the workstation through a terminal. This is how the IED cluster looks like. On the one side, a driver of the OPLRT simulator manages the IEC61850 data exchange, which is configured using IED capability description files. On the other side, the IEDs can communicate also through an open source library for the IEC61850. This is how the network connections looks like. A network sniffer such as Wireshark allows us to analyze the information flowing through this network. Data exchange was done through IEC61850 communication standard, which is a standard meant to create an interoperable environment in digital substations. It is also considered a fast Ethernet protocol, which allowed us to obtain satisfactory performances in terms of speed for the non-selective protection strategies. As mentioned before, we used IEC61850 both on HyperSIM and Raspberry Pi based IEDs. This is a good example of interoperability, since 2 different pieces of hardware, which are the OPLRT target and the Raspberry Pi computer, were able to exchange data through a common protocol implemented differently. This was not straightforward though. A good comprehension of the norm semantics is required, as well as a clear definition of the functional architecture of your system. Then provide unique identification for each communication link. On the other end of the HIL tests, we find the intelligent electronic devices prototypes. We used Raspberry Pi to prototype the IEDs. We used C code programming language because of its flexibility and execution speed. Also, with a well-structured coding approach, we can ensure modularity. With this, we can instantiate this program anytime we need to create a new IED or make developments. One of them is the protection IED. The C code was written based on the specifications provided in Work Package 4 or from interpretation from Simulink blocks like in the FBS case. We first tested the program in HyperSIM, where the code runs in synchronism with the simulation. Then we imported this code in the Raspberry Pi based IED for HIL tests. Similarly, we developed supervision IEDs. Supervision algorithms are generated from Replica, a software to design automation systems using discrete event system theory. This is an example of results we obtained for the CBS strategy. A fault is applied in the middle of cable 2-4. The graphs here shows a fault happening at 4 seconds, being cleared about 20 milliseconds after that, and the system being restored around 200 milliseconds after. The bar on the right hand side shows goose messages observed with Wireshark during the whole process. In summary, the main objectives of WP9 were assessed for both CBS and FBS strategies. HIL tests were performed using RTS models developed in HyperSim to build up 2 4-terminals HVDC networks. IEDS for protection and supervision were tested, and we could perform primary and backup sequences for different fault test scenarios. Using IEC 61850 communication standard for these tests showed that 2 different pieces of hardware were able to exchange comprehensive data for the application of protection and supervision. After promotion, we will continue working on this HIL demonstrator. First, we need to automatize the simulation procedure and reporting so that we are able to perform more simulations and get the necessary amount of data to calculate performance indicators and validate the robustness of the strategy against communication issues, for instance. Also, we need to keep maintaining and upgrading the HIL demonstrator. We can work on adding more features to the IEDs, such as creating better debugging methods. We also want to increase our test environment, which is the real-time simulation. We have to continuously improve our existing models and upgrade the benchmark grid to study the impact of protection strategies to different kinds of networks that can be connected to an HVDC network. And last but not least, we are moving towards the implementation of a communication network that is as closest as possible to those we find in digital substations. This includes the human-machine interface, different communication protocols, routers to emulate communication between distant substations, and so on. Thank you very much for your attention. The complete demonstration will be available in Promotion's official YouTube channel. A link is available from the Promotion website.
So my thanks to the other presenters. It's now back to myself, Ian Cowan, and I'm going to first talk about the demonstration of partially and fully selective DC grid protection strategies, and then go on to say about the work package key conclusions. So first, a little on the test environment that we used. This again was all done in real time, where the guys at SuperGrid used Opal RT, we used the RTDS system. But again, it's similar in that it's a closed loop simulation environment, and that lets us check the dynamic response of the overall system. And also it meant that we could test multiple devices simultaneously and check that interoperability. And it's just a more detailed system representation than an open loop equivalent. For us, the AC networks were modeled in the so-called large time step with a similar 50 microsecond time step that was used at SuperGrid. But for us, with the partially and fully selective schemes, because they're that bit quicker, the full DC network, including the converters, was all modeled in the small time step. So that was about 4 microsecond time step we used in there, with full frequency dependent cable models used, so that we could see the fast approaching that the IEDs would be expecting to see in real life. The base 3-terminal network radial was based on the Caithness Murray Shetland scheme. So on operation just now, Caithness Murray has a point-to-point link, and that has had the green light now to expand to the first European HVDC grid with the expansion to Shetland. So that was the basis of the model, but for the subject of this testing, we expanded that to include the mesh that you can see in the bottom right. Everything that's on the single line for most of the testing was modelled in the RTDS, and then it was the DC voltage and currents fed out to the vendor IEDs, and then the breaker commands coming back in. So that was the test setup that was used. More details about the model are available in deliverable D9.1. So the IEDs that were under test here was the promotion IED developed within Work Package 4, but also a vendor supplied the IED some key differences between them is that the vendor supplied one is using their state-of-the-art technology, and maybe the photo doesn't give you that good impression, but it's a very different scale to the promotion ID. And this is something that would be ready to be installed in a substation today. So the test method was of course informed by D9.2, where we did faults at different steps on the line with different fault types and did repetition so we could get an average, and we recorded all the key performance indicators as we went along. So I don't have time to go through the full results, but here's an example from some of the partially selective testing that we did with just the single breaker and IED in operation for each time. You can see some example time domain results on the right, and at the bottom you can see the IED times for the full length of the line for all the different repetitions of the fault. So you can see that's well within the 2 millisecond target that I mentioned earlier. So in each case, this was a single vendor, but we did this for each of the different breaker types with each of the IEDs in turn and saw a similar and adequate performance throughout. Once we move to the fully protective protection scheme, the picture's not very clear unfortunately, but you can maybe make out we had different breaker types spread throughout the model. So we've got for the hybrid breaker, we've badged that with the ABB as it's their design. For the mechanical breaker, you can see the Mitsubishi Electric logo again, but also we've got the Cybrake breaker design in there as well. And pointing at these breakers, we've either got a promotion IED controlling their switching or the Mitsubishi Electric IED controlling their switching. From the runtime, this is where we could control the fault type, which cable the fault was on, and then we could set up the automated testing using a script to run through all these tests to get a good understanding of the performance of the IEDs and of course the overall test system. By using this mix of different technology devices and IEDs, it really let us push the multi-vendor aspect while also assessing the primary and backup protection in terms of system level KPIs. Now, there'll be more details of that given at the demonstration event on Wednesday 9th, or if that's passed, then there'll be some available information on the website based on that. So in parallel to using the sort of generic converter models, what we have here at the HVDC Centre is the replica control and protection cubicles for that Caithness Murray Shetland scheme that I mentioned earlier. So what this means is for the full single line is still modelled in the real-time simulator, but the controls of the converters are now actually replicas of the real system. So it's a similar setup to the IEDs where you feed out the system voltages and currents, but in this instance we're getting the firing pulses for the valves back in, and that's how that's in the loop for this real-time testing. So in this instance, we used the replica model as a basis. It's a much more complicated model as there's much more input and output. It wasn't immediately suitable for this testing as it was never designed for doing DC protection testing, as there's not currently a DC breaker in the scheme as it's designed. So we had to start with that original replica model and move the element with where we're introducing DC breaker and the line into the small time step frequency dependent model so that we could assess the IED performance. It let us check another type of interoperability, so we're combining the physical IEDs with physical control hardware. Important to point out, we didn't actually change anything in the control hardware of the link, so everything that we observed could possibly be improved upon, but also it's quite reassuring to know that with a system design that was existing, we managed to get the IED to perform similar to the testing with the generic models, but also that we could continue point-to-point operation for a fault on the third line based on this protection scheme integrating without any additional works on the controls. So it just goes to prove that the protection system designs is adequate for a current scheme and could readily be introduced. It also meant that we could subject the IEDs to normal system activities. So when we're using the replicas, and part of the reason we can use this for the extensive testing is that we had to run through the normal startup and shutdown sequence using the replica interface, and this meant that we subjected the IEDS, as I say, to a full startup sequence, and they rode through them without doing any spurious trips. So that's further confirmation of the viability of these protection system schemes. So in summary for this bit, we've demonstrated successfully the operation of fully and partially selective protection schemes on the most realistic test case we could do without actually putting it on a real system. And the key takeaway, I suppose, is that the IED's performance is expected to be sufficient for potential future HVDC grids. Through this, we evaluated the interoperability, looking at multi-vendor protection systems, and we've developed real-time models that can be used for benchmarking performance of real IED devices using hardware and load testing. And we did this by integrating the DC protection systems designed in Work Package 4, along with the IEDs and the DC breaker models from Work Package 6. I say, if you're watching this before September 9th, please do sign up to the final demonstration event. The link's at the bottom, and join us for the full detailed results. So overall for the work package, it demonstrates successful operation of all the different types of protection schemes, so fully, partially and non-selective. And through all that, the IEDs performed as expected and are sufficient for potential future HVDC grids. Interoperability was looked at in a number of different ways by combining different types of breakers with different technologies, but also with the SuperGrid work starting to look at the use of IEC 61850. We've created a prototype system supervisor for the non-selective protection scheme, and we've developed real-time models for both the RTDS platform and the Opal RT platform that can be used for benchmarking performance of IEDs across the different protection system schemes. And of course, we've got the test procedure that can be used as a standalone for assessing the primary and backup DC grid protection. So I think it's fair to say that the journey is not over, but we've taken some great strides towards having a DC protection system that is ready to go. And I think even if it's not available right this minute, I think for the DC grid of tomorrow, we're ready to provide a DC protection scheme that you can trust. Thank you for watching, and thank you to all my presenters and everyone that's contributed towards Work Package 9 and its outcomes. Thank you. Just a final note to say that these videos are being released on the Monday, and of course, if you have any questions, you can direct them to us directly here, or on Friday there is a live Q&A session, so please do sign up to that on the promotion website, and I'll hopefully see you then. Thank you.